Good morning. Good morning. Is it audible? Good
Good
morning.
morning, sir.
Good morning. Shall
Good
we
morning,
start?
sir.
Shall we start?
Yes, sir.
I stopped at this point. We have discussed uh, starting from state of stress, 9 stress components. In one dimension, stress is uniform, and once only sigma x or sigma comes into picture. When you take a body, there are infinite number of points, and at each point, I can pass infinite number of planes. Transformation in the sense from one coordinate system to another, we are transforming. For that, what is the stress on other coordinate system, we will find with reference to the given coordinate system. Okay, this transformation, and this is the representation of stress. X tau xy, x indicates the normal to the plane, y indicates the direction of stress. And we discussed what is meant by plane stress condition. And then we discuss what is meant by principal stress, maximum shear stress. And then we have discussed about a condition when there is a plane, when there's plane has a certain inclination, for the state of stress going different. Okay, let us go ahead. I would like to give some sign convention before starting. Always normal stress, that is sigma x and sigma y. Normal stress acting away from the body or tensile in nature is positive. I will discuss this next. Shear stress how can I define? Give me a moment. If I write like this, shear stress, okay, on positive planes and positive direction or negative planes and negative direction is considered to be positive. First, I will talk about this. Always normal stress sigma x, sigma y acting away from the body at R tensile in R, not ERR, R tensile in nature is positive. For example, if I consider this is sigma x, it is acting away from the body, R which is tensile in nature is considered to be both sigma x and sigma y are positive. Sigma x is positive, sigma y is positive. Okay. Next, coming to shear stress on positive planes. If this is the shear stress, if there is shear stress like this, and then in the opposite plane, opposite surface, you should write an opposite arrow, and this arrow should meet here, and this arrow should meet here. It means to say that shear, this is the positive plane. The normal to this plane, this is the positive plane, x is the positive plane, and then this is a negative plane, negative x. Okay. For example, if I write tau xy, normal to the plane, normal to the plane is in positive x direction, and stress is acting, stress is acting in positive y direction. This is this condition. When I come to here, normal to the plane, tau xy, normal to the plane is in negative x direction, and stress is acting in negative y direction, negative y direction. This is also positive. Okay. Similarly, tau by x, normal to the plane is in the y direction, stress is acting in x direction. This is positive. Normal to the plane is in negative y direction, stress is acting in negative x direction. That is also positive. Generally, what you should know is shear stress acting, which is causing, if you consider this like this on normal to, if this is the x, normal to the normal is in x direction. If the arrow is pointing upwards, this is tau. If the this is tau. This now, if the arrow is pointing upwards, this is the positive shear stress condition. This is the positive shear stress condition. In case, if the shear stress is acting like this, this is negative shear stress. For example, if he has given tau is equal to 30 MPa, this is positive 30. This is tau is equal to minus 30 MPa, negative 30. Because you can see normal to the plane is in positive x direction, tau xy, if I write. Normal to the plane is in positive x direction, normal is in positive x direction, but the stress is acting in negative y direction, negative y direction. Hence, this stress is negative. Similarly, normal to the plane is negative x direction, but the stress is acting in positive y direction. This is negative. Both the signs are positive or negative, you can say both the signs of normal and the direction are positive and are negative. You can say that the stress is positive. Okay. If it is positive or negative and positive, then the stress condition is negative. Okay, this you should know. Only the thumb rule is, if the stress is pointing upwards, you remember that there is positive stress. In case like this, on the right hand face, not on the left hand face, it is pointing upward, is positive. In case if the stress is like this, sigma y, sigma x, okay, and sigma x, both sigma y is negative and sigma x is also negative. Or sigma x can be positive or sigma y can be negative, whatever it can be. But what we should remember is, when both the normal and the direction are in positive sense, or both the normal and the direction are in negative sense, then the stress is positive. If one of these is negative and positive, then the stress is negative. Okay, this you should remember always. This should point upwards. Then only your stress condition is positive. Okay. Next, let us uh, obtain uh, now let us obtain the stresses for there is a normal and tangential stress for a member subjected to in plane loading. There is a uniaxial stress. Okay, let us consider a bar subjected to uniaxial loading. That is along the length of the bar. Loading is along the length of the bar. Stresses are 1D. When you say the stresses are 1D, generally we write sigma is equal to P by A. This is responsible for failing. No, when for ductile material, this stress is not responsible for failing. We'll see in future what is responsible for failing. Whether it's a shear stress or the normal stress responsible for failing, we'll discuss later in this class and next class. Okay. Now, when I say like this, if there is a section, if there is a plane like this is when I talk like this, if this is the member. If there is a plane like I'm interested in a plane like this is the member. I'm interested in plane at certain angle from this theta. I will discuss the sign convention later. I'm interested in a plane like this. This plane I'll call it as G E. This is the plane. This is I'll call it as H. Okay, the body is a long slender member, is a bar. In the bar, if I take the stresses throughout along the length, the stresses are uniform. But if there is a plane which is at a certain angle in that bar, then the stresses are different. I need to find the stresses on that bar. As soon as you write a bar like this, you assume it is 3D like this. It is 3D like this. It is 3D like this. Okay, and also there's thickness in this direction also. This is the section I've taken. This thickness is of 1 unit. Okay, this if I call G, this is H. Thickness is of one unit. Give me a moment. This inclination is theta. Okay, I need to find stress on this plane. I need to find stress on this plane. What is the stress on this plane? Whenever I take a plane, along this plane, I can write my this instead of P, I will write sigma x. Okay, that one and the same, sigma x. Whenever I take a plane like this, I should resolve the forces. One is perpendicular to the plane called as normal stress. One is along the length of the plane called as tangential stress. This plane is called as normal plane. This plane is called as tangential plane. For equilibrium, when I take a plane, there are two stresses induced. One is the normal stress and the other is tangential stress. There is also one more stress, that is a shear stress. Since we are talking about 2D, we're confining ourselves with respect to normal and tangential stresses only. So when we should remember that whenever I take a plane at certain angle, along the length of the member, along the length of the plane, there is one stress induced called as tangential stress, and perpendicular to that plane, there is one more stress induced called as normal stress. Okay, keeping that in mind, I will write this in 2D. Since thickness is 1 unit, if I call this as G H E, this is perpendicular. This is the normal stress, and the plane is called as normal plane. This is the tangential stress, sigma t, and the plane is called as tangential plane. Okay, and the load, instead of sigma x acting here, I'm taking load acting to be like this, sigma x. Okay, are you able to understand up to here? Are you able to understand up to here?
Yes, sir.
Right? No, it is a little difficult for some time until I do two or three cases. Little difficult. You will get used to this. Don't worry. Okay. No. Now, sigma x, I can write. Instead of expressing it as stresses, I will express it as forces. I'll express this as F. I will express this as Fn. Instead of sigma n, I will express this as Fn. Instead of at sigma t, I will express this as ft. This is the normal plane. This is the tangential plane. Okay. Next, this is 90 degree. Next, see, I can write sigma is equal to f by a or p by a. Sigma into a is equal to f. So this sigma x into area is gh into 1. This area is gh into 1 unit. This is 1 unit. This gives your f. Similarly, I can write fn is equal to sigma n into that area GE into 1 is equal to Fn. Similarly, sigma T into GE into 1 is equal to Ft, which is what sigma x into GH, sigma n into GE, sigma T into GE. This is Fn and Ft. Okay. Now I have taken this force. This is at an angle theta. This is at an angle theta. We have discussed in the previous class. If I write x plane and a y plane like this is my write in another color. This is my x direction. This is my y direction. This is making an angle theta. An angle theta. You can take alternate angles like this. If this is theta, if you take like this will also be theta. This will also be theta. Don't worry about that. This will also be theta, isn't it? If you take a perpendicular like this, you can take. We will discuss later. Now I will draw a line. I want to resolve. See, my ultimate aim is to find the stresses on this normal plane. I want to resolve the forces in such a way that I want to find the stresses on this plane G. I want to find the stresses on this plane G. I know the stresses on this plane. I know the stresses in, for example, if I say ABCD, I know the stresses on this plane ABCD. I know on this body stresses on this body ABCD. I want the stresses on this plane G. So in order to know the stresses on this plane GE, I have two components. There is a normal component and tangential component. Always the stress is defined with respect to x and y axis. That is perpendicular to the surface. In this case, the perpendicular to the face is sigma normal and sigma tangential. Perpendicular is normal. This is the normal, and the other perpendicular the axis is sigma tangential. Instead of x and y, for this inclined phase, it is sigma normal and sigma tangential. Okay. Now I want to resolve the stresses in such a way that I want the stresses on sigma normal, there is a normal phase and tangential phase. Okay. I want the stresses on normal phase and tangential phase. But this stress I want to resolve, this force I want to, this sigma x, I want to resolve along sigma in normal phase and tangential phase on inclined plane. This GH on inclined plane. GH. This is G, inclined surface G. Okay. Now this is f of n acting like this. F of t, I will draw. This is parallel to f of t. I will draw like this, parallel to f of t. This is like right, drawing f of t once again like this, or I will draw like this. Then now n and t are perpendicular to each other. If I say this is n axis, this is t axis, this is perpendicular. If this is theta, this is perpendicular. This will be 90 minus theta. 90 minus theta. Right? Since my f is pointing, I want to resolve my f. I want to express my f along normal and tangential basis. This is my f is acting like this. My f is acting like this. This is my f. Instead of taking f, here I am taking f here along the x-axis. F is acting like this. This is a resultant. Therefore, this should act like this. This should act like this, isn't it? This should act like this. This should act like this. But f of n, when I resolve, when I take, when due to load p or due to stress sigma x, when I say, you should remember this. When I resolve the force sigma x, For equilibrium, there are two forces on this plane, sigma n and sigma t, that will act when you take the section itself. There are two mutually perpendicular stresses, sigma and sigma t, acting on this plane. Okay, this sigma n and sigma t, instead of sigma n and sigma t, I have written as f of n and f of t. Okay, let's write properly. Okay, now if this is the force f of n, and instead of sigma and sigma t, I have expressed it as f of n, f of t, and f. Okay, when I resolve it, when I take a plane for equilibrium, there should sigma and sigma t automatically comes into picture. Okay, when I take this is f, for resultant force, this is the resultant force. This is f sin theta. This is f cos theta. Right? Opposite to theta is f sin theta. This is theta. Opposite to theta is f sin theta, and then this adjacent is f sin cos theta. For equilibrium, summation of normal forces should be equal to 0. That I can write it as f of n. This is along the normal direction. Along the normal direction, this is positive. Along this small n direction, this is positive. F of n. Okay, this is the normal direction. This is the tangential direction. You can understand this. This is the normal direction. This is a tangential direction. F of n. F of cos theta is acting opposite f of n minus f cos theta is equal to 0. Okay, or f of n is equal to f cos theta. Now f of n I will represent in terms of stress. Sigma n into g f of n. Okay, sigma n into g is equal to f is equal to sigma x into gh into cos theta. Okay, have you understood this up here? If you understood this, everything is simple. Everything holds same. The concept is same. Okay. Next, we have written sigma into g is equal to sigma x into gh cos theta. Right? Sigma n into g is equal to sigma x into gh cos theta. Or I will write, I want the normal stress. I want my sigma x to be represented as sigma n and sigma t. I want to find an expression for sigma n and sigma t in terms of sigma x and theta. Okay, I can write sigma n into sigma x by gh by ge cos theta, or sigma n, which is equal to gh by ge, gh by ge, it is nothing but adjacent by hypotenuse. This is gh, this is ge, adjacent by hypotenuse, which is nothing but cos theta, sigma n into cos theta into cos theta, or sigma n is equal to, sigma x into cos square theta. This I will call it as 1. Next, we have resolved the forces along the normal direction. Similarly, we want to resolve the forces along tangential direction. F of t is equal to 0. F of t, this is a tangential direction. F of t is all the same. There is no force F of t, but the force is active. There is no force along the tangential direction. Only the force is along the horizontal direction. But as soon as we resolve that, we will get normal component and tangential component. Okay, this f of sin theta is along the tangential direction. Can I write sigma f of t is equal to 0, or f of t plus f sin theta is equal to 0? Isn't it? F of t, my f of t is in this direction. F of t is in this direction or in this direction. Okay, f sin theta is also in this direction. There is no f of and there is no other force component. Only tangential, and this component, when I resolve it, I will get f sin theta, or f of t plus f sin theta is equal to 0. Or I can write f of t is equal to minus f sin theta. f of t is equal to sigma t into g. Sigma t into g is equal to minus f is nothing but sigma x into gh. Sigma x into gh sin theta, or sigma t, which is equal to minus sigma x gh by ge sin theta, or sigma t, which is nothing but tangential stress. Sigma t is nothing but tangential stress. Gh by ge, gh by ge is once again cos square theta. Sorry, gh by ge cos theta, cos theta sin theta, sorry, cos theta sin theta. Sigma t is equal to sin 2a is equal to 2 sin a cos a, or minus sigma x into sin 2 theta by 2. Okay, this can also be written as tangential stress tau. Okay, this I'll call it as second expression. Second expression. Okay, now uh, we have derived this. We want to find the principal stress. Isn't it principal stress and the maximum shear stress? How to find? This is by inspection. This is by inspection. First, I will take the normal stress. Sigma n is equal to sigma x into cos square theta. For what values of theta this will be maximum? Theta can range from 0 to 1 only. This will be maximum only for, give me a moment. Okay. This will be maximum for theta is equal to 0, or theta is equal to 0. Theta is equal to 90. Cos theta is equal to 90. Okay. This is maximum. And what are the other angles? 90, 180 is minus 1, 90, 270. But we will get one angle. Give me a moment. Sorry, give me a moment. I made a mistake here. Theta can range from I can say theta ranging from 0 to 1. I'll send you the second link. Last 10 minutes remaining. Theta can range from 0 to 1. Therefore, sigma n, or sigma n to be maximum, our theta should be equal to 0. If theta is equal to 0, sigma n is equal to sigma x. This is the maximum value of theta which you can get. Okay. Always you should remember that. There are three principal stresses, and sigma is minimum. Sigma is minimum in the sense that for theta is equal to 0, this is the maximum value. This is the maximum value. Max value. Minimum value is nothing but 0 only. That is for theta is equal to 90. Theta is equal to 90. Sigma n is equal to 0. Okay. Instead of maximum value, I will call it as sigma 1. Minimum value, I will call it as sigma 2. These are called as principal stresses. The maximum principal stress in case of a bar subjected to uniaxial loading is sigma x itself, that is the same P by A, and the minimum loading is sigma 2, that is equal to 0. Okay, this we should keep in mind. Okay, next we'll go to maximum shear stress, which is given by tau or sigma t, which is equal to minus sigma x into sine 2 theta by 2. Okay, the maximum value for this will be, let me write, the maximum value of theta can be 2 theta should be equal to 90 degree, therefore sine theta will be 1, therefore tau is equal to sigma t max or tau max, sigma t max, which is equal to minus sigma x by 2. Minimum value is minimum, this shear stress in the sense this is complementary, or I can write tau is equal to minus sigma x by 2, or I can write plus 2 theta is equal to 90 degree, or give me a moment, this type if I call instead of this, theta s1 is equal to 45 degree. I'll explain this. Theta s2 which is equal to 45 plus 90 is equal to 135, 2 theta is equal to 270. Okay, I'll explain this, don't worry. Sigma t or tau minimum is equal to sigma t minimum, which is equal to minus sigma x into sine 270 by 2, which is equal to sine 270 is minus 1, which is equal to sigma x by 2. Okay, this can be maximum or minimum, don't worry. This is, if this is minimum, this is maximum, don't worry about the sign. But you should remember, sign indicates that it is acting in the opposite direction, that's it. Always you should remember that. Or shall I send you the once again the link? Always you should remember that there are 3 mutually perpendicular principal stresses. Or in case of 2D, there are 2 mutually perpendicular principal stresses. Each is 90 degree with respect to each other. For example, if I say theta is equal to 0, this is the maximum, this is the plane of maximum principal stress. This is the plane of maximum principal stress. Theta is equal to 0. Theta 1 is equal to 0. Second principal stress is nothing more, is at an angle of 90 degree. Therefore, theta 2 is equal to 0 plus 90 degree. This is theta 2 is at an angle of 90 degree. Okay. Similarly, when I take shear stress, theta s1 for maximum value of this 2 theta should be 90 degree. Therefore, theta s1 means 2 theta s, if I write theta s1 should be, generally I write 2 theta s for writing this. If I write individually, theta s1 should be is equal to half of this 45 degree, and then theta s2 should be, theta s1 is equal to theta s2 is equal to theta s1 plus 90 degree. It means that my shear planes are mutually perpendicular to each other. They are at an angle of 90 degree with respect to theta s1 is at 0 degree some angle. Theta s2 will be 90 degree to that one theta s1. Similarly, principal stresses are mutually perpendicular to each other. If theta 1 is at some angle 10 degree, theta 2 will be at 100 degree. Okay, that you should understand. What I have done, I have for me to get maximum value of sigma n, I have substituted theta is equal to 0. Then sigma n will be equal to sigma x. Then what is the minimum value of sigma n? You can get it. You can add theta 2 as a theta value. You can think and you can do also. But generally, we always have, there are 2 mutually perpendicular planes, theta p1. If I call this as theta principal plane p1, theta p2, which are mutually perpendicular to each other, and they are separated, or you can see they're separated by 90 degree. Theta p1 and theta p2 separated by 90 degree. If theta p1 is at 0 degree, theta p2 is nothing but theta 1 plus 90 degree. So this 0 plus 90 degree, theta p2 is equal to 90 degree, and this magnitude is sigma 2 is equal to this sigma n. If you substitute 90 degree, you will get 0. Similarly, the maximum shear stresses from inspection I found out the maximum value of 2 theta can be 90 degrees, so that my sine will be 1. And then if I substitute here, I'll be getting tau max equal to minus sigma to by 2. If I write, in case if you want for clarity, you can write it as tau minimum. This can be tau maximum, or whatever. What you should understand, whether it's tau minimum or tau maximum, the magnitude remains the same. The magnitude remains the same. Only the sign changes. Okay. What does this change sign indicates? I will discuss in the next class. So what does the sign indicates? I will give. I will tell in 2 minutes. This sign indicates. This sign indicates my sign. If you see this, my shear stress acting, which was causing, on this was the explain, unexplained, it was causing anti-clockwise movement. My shear stress was causing anti-clockwise movement. In case my shear stress tau sigma t or tau is positive, it means that it is causing anti-clockwise movement. In case if it is negative, it means that on x phase the tau is not acting in the upward direction, it is acting in the downward direction, it is causing clockwise movement. When we solve the problems, we'll come to know. But time being, for representation, when I represent it, we'll come to know. Okay. Now I'll represent it in the next link. Next class I'll represent it. You'll come to know. You should understand that there are normal stresses. There is a principal stress 1 and principal stress 2. Each are separated by 90 degrees. The maximum value of principal stress for a bar subjected to uniaxial loading is sigma x itself. That is equal to sigma 1. Minimum stress is sigma 2. That's equal to sigma. That is equal to 0. But you can see tau max or tau minimum. Tau max is equal to tau max or tau minimum. Tau max or tau minimum, it is equal to sigma t max or sigma t minimum. Sigma t max or minimum is equal to plus or minus sigma x by 2. It means to say that this is failing if I load the body, if the maximum load which it can withstand is sigma x. Forget about sigma 2. There is nothing but sigma 2. There are no stress. It means that there is no stress. The maximum stress when I apply the body, the maximum stress the body can withstand is sigma x. If you feel that the maximum stress is sigma x, you are wrong. See, from this we can inference that the maximum or minimum stress is half of the sigma x, half of the uniaxial stress. When you load the load the bar in tension, it will not fail due to your axial loading, that is sigma. It will not fail to sigma x stress. It will fail due to shear stress, because the shear stress is half of the uniaxial loading sigma x by 2. That is why ductile material fails when shear, because they can withstand only half of the load only. Compared, generally it can be, this is called as Tresca theory. Tau max is given by sigma yield strength by 2. The maximum strength that can back on withstand is half of the yield strength. Okay, this is the inference. That is why we are doing this. Whether it will fail by tension or compression. Okay, we need to know that. Okay, from this it is inference that only half of the load in axial loading can be withstand in shear stress. Okay? Another only 1 minute remaining. I'll stop at this point. In the next class, I will represent it. It looks a little difficult. Many concepts are involved. 1 or 2 derivation will understand this. But time being, I will explain once again. Will come to know. Okay. I will stop at this point. I'll send you the second link.